Hi everyone. Today in this lecture, I want to solve another example to show you how you can solve a circuit in Laplace domain. Here you can see a circuit, and in this circuit we do have a switch. And this switch shows us basically the circuit before zero and after zero. Let me draw the circuits before zero and after zero, and then we can discuss what we need from the circuit before zero and how we're going to use the circuit after zero. So before zero, the switch is at A, so this is what we have before zero. So I can draw my circuit in this form. I have the 500 volt voltage source connected to this 5 ohm resistor, and then I have the inductor, the other resistor connected in series all together. So here is the 25 Henry inductor, and then 25 ohm resistor. And then on the other side of the circuit, I do have this 100 ohm resistor connected to my capacitor. So this is my circuit before zero. Now, in circuit after zero, what do I have? In the circuit after zero, this time I have switch here. So it means that these elements are all connected, and the source and the resistor here are disconnected from my circuit. So my circuit after zero has the inductor, resistor in series, and then connected in parallel to another resistor, and at the end I have the capacitor in parallel. So this is my circuit after zero. Okay, now the question is that what I'm going to do with the circuit before zero and what I need to do with the circuit after zero. Why I need the circuit before zero? I need the circuit before zero for only one reason. And that reason is that I need the circuit in order to find my initial values. And then I have to use my circuit after zero for Laplace domain. So I have to transfer the circuit after zero into Laplace domain. So this is the circuit that I have to focus when I'm trying to prepare my circuit for Laplace domain. And now I'm going to go to circuit before zero, and I'm going to find my initial values here. Then I'm going to use them for the circuit after zero. Now let's go to the initial values. For initial values, what I know is that because it's before applying the change, before changing the location of the switch, it means that the circuit before zero is a stable circuit. It means that I can short circuit my inductor and I can open circuit my capacitor. And now I should be able to solve this circuit before zero to find my initial parameter. What are initial parameters? The initial parameters are the voltage of capacitor before zero and the current of inductor before zero. So these are equal to, the voltage of capacitor is equal to zero, because on the circuit I have in right hand side here, there is no source. So it means that the voltage of capacitor at the end would be equal to zero, because even if there is any voltage, because it will be completely discharged, there is no source of energy. So the voltage of capacitor before zero is equal to zero. However, because on the other side I do have a source, I'm going to have a current for my inductor, and the current is equal to this 500 divided by 5 plus 25 and it's going to be equal to 16.6 amp. So now I know that for the circuit after 0, the voltage of capacitor is equal to 0. So this is my initial condition that I can adopt for the circuit after 0. And also, the current of inductor after 0 is equal to this 16.6. So I can also use this one in order to prepare my circuit for after 0. Okay, now let's draw the circuit after 0 and find its equivalent circuit in Laplace domain. So I'm going to quickly draw the circuit after 0 in time domain. So this is my circuit before 0, and for this circuit I have the voltage of capacitor, which is my initial condition, as 0, and the inductor's current equal to 16.6 amp. Okay, now I want to draw my circuit in Laplace domain. In Laplace domain, I have to take care of my sources and inductors and capacitor. So those are what I need to describe them correctly with their correct equivalent function and equivalent circuit in Laplace domain. Here I don't have any source, so I don't need to take care of that part, but I do have the capacitor here and inductor here, so I need to use their equivalent circuit. The equivalent circuit that I'm going to use for capacitor is only one component, one capacitor, because its initial voltage is equal to 0. So I don't need to have the series or parallel voltage or current source. But for the inductor, I need to have the voltage source or current source as series or parallel equivalent circuit, because I do have some initial values for the inductor. So what I'm going to do is that I'm going to go with the series equivalent for inductor. So I'm going to use the series equivalent, and you should be able to tell me why I'm choosing to use the series equivalent, because the inductor is in series with the resistor, so it's easier to have everything in series. So I'm going to go with series equivalent here. So I'm going to have the inductor and then its voltage source, which is supposed to be L multiplied by initial current. So I have the voltage source here, and then I have the resistor at the end, and I have the capacitor and resistor in parallel. So this is my circuit in Laplace domain. Now, what are the values? The resistor are going to be the same, so 100 here and 25 here. For inductor, I have to go with LS, so I have to use LS, so it's going to be 25S. And for capacitor, I have to go with 1 over CS, so the impedance is going to be 1 over CS. Now, C is equal to 10 to minus 2, so 1 over 10 to minus 2 multiplied by S is going to be 100 over S. The last component to take care of is the voltage source that models. So what I have here basically model the inductor. So the voltage source I have to use here should show me the same direction for the current as the initial current. Going back to the circuit before 0, the initial current that I had here was in this direction. So in this direction. So it means that I need to choose the voltage, the positive here and the negative here, so the current comes out of the positive and it would be in the same direction as initial current. Okay, so this is my voltage source, and then the value of this voltage source is equal to Li naught. L is equal to 25. The initial current is 16.6. So if I multiply them, it's going to be 416.6 volt. So let me erase this one here. Okay. So this is the value of my voltage source. Now I have my circuit completely prepared to be solved in Laplace domain. So now here I'm going to go to the next step, which is solving the Laplace domain circuit for whatever I was looking for. Let's go back to the original circuit and see what I'm looking for. What I'm looking for here is the current of capacitor, which I'm calling it as IO. So I'm looking for this current, which is IO. I'm going to solve the circuit using nodal analysis. So I'm going to choose this node as my reference, and I'm going to call this voltage as V. So I'm going to solve for V, and then when I have V, I can use Ohm's law for impedances and find the current of IO, which is the current of capacitor. Okay. In order to write KCL here, I have 3 different currents that are leaving this node. These two are pretty straightforward. The only one that is a little bit more difficult is the one for this particular branch, the branch with inductor. So what I'm going to do is that I'm going to swap the location of these two because they are in series. Then it's going to be easy to describe the current. It's going to be the voltage here, V, minus 416.6. So minus is going to be plus. Let me write it in the next page. So if I write KCL for V, I'm going to have V plus 416.6 divided by, don't forget that you have to include all the impedances in this branch, so you have to include both 25S and 25. So divided by 25S plus 25, and then I'm going to have the current of this branch, it's V over 100, and the next one is V over 100 over S. So plus V over 100 plus V over 100 over S equal to 0. So this is what I'm going to have as KVL, and as you can see, I have only one unknown parameter, and that's V, so I'm going to be able to solve it. In order to solve this equation, what I'm going to do is that first I'm going to multiply everything by 100 to get rid of these hundreds here. So I'm going to multiply everything by 100. Then I'm going to have 4V plus 1666.6 divided by S plus 1 plus V plus S multiplied by V equal to 0. In next step, I'm going to describe these two as V multiplied by S plus 1, and then I'm going to multiply everything this time by S plus 1 to get rid of the denominator here. So I'm going to have 4V plus 1666.6 plus V multiplied by S plus 1 S squared equal to 0. So now what I'm going to do with this equation is that I'm going to keep those terms with V in one side and all the constant on the other side. So I'm going to have V multiplied by 4 plus S plus 1 squared, and on the other side I'm going to have minus 1666.6. So it means that my voltage in Laplace domain is equal to minus this constant number divided by S squared plus 2S plus 1 plus 4, which is going to be 5. And in order to find my current, which is IO of S, I have to multiply my V of S by, I have to divide V of S by the impedance, which is 100 over S. I'm going to show you the solution in next slide.